Hey guys, hope you're having a good day. I've got a question here, which I typically like to go through with my students. And I wanted to just share with you how I normally break down a GAMSAT style question. I usually will ask students to go straight to the question rather than trying to read all of the context. There are a few reasons, but the main reason that I find it's effective is that once you've read the question, you'll have a better understanding of what to look for. Okay, so what's actually relevant. So let's kind of jump straight into it. Question 66, which of the following is least likely retained in the atmosphere of the Earth? And now what I would do is I would look up at the information provided. I'll probably start from the beginning, to be honest. A few things that I will note. Like it's already mentioned Earth, and I can see that that's in the table. Okay, so I can start linking the question to the information already. And it's talking about least likely retained. And I can see that although it doesn't directly relate, or it doesn't directly reference to anything in the question, or in the information above, I should say, that it does talk about escape velocities. And something that is least likely retained is probably the most likely to escape. So it's just another way of saying most likely to escape. So what I'm trying to do is I'm trying to frame the question in such a way that it directly relates to the information that's being provided. Okay, so which of the following is most likely to escape? And what are we talking about here? Hydrogen, helium, argon, and xenon. Most likely we're talking about gases, and they do talk about that. They do mention gases. Okay, so which of the following gases is most likely to escape? So reading the question and having a brief look at the information above, I get a better picture of what it is that it's asking. So let's have a look at what the escape speed is. So let's have a look at the first paragraph. It says the escape speed from a celestial body is the speed that must be attained by a particle on the surface of the celestial body in order to escape the gravitational pull of that body. Now that is a bit of a mouthful for most people, and it can be difficult to digest. And a tip that I usually give people is to try to replace certain words with things that are a bit easier for you to wrap your head around. So for example, the escape speed from a celestial body. Now, hopefully you guys know what that's talking about. It's talking about planets, essentially, and you can see it does mention planets. So we could just change that to planets. Okay, so the escape speed from a planet is the speed that must be attained by a particle. So in other words, the particle must have that speed to be able to escape the gravitational pull of the body. So in other words, you need to be traveling, let's say you're the particle, you need to be traveling at a certain speed, which is the escape speed, to be able to escape from a certain planet. Okay, that's what the escape speed is. It's almost like a speed limit. You need to reach that speed to be able to escape. Okay, let's go back to the question now. So, which of the following is most likely to escape from the Earth? Now, if you look at table 1, it mentions that Earth, and also look at the reference, it says that table 1 tells us the escape velocities for various planets. So for the Earth, the escape velocity is 11.2 times 10 to the 3, it's up there, meters per second. So in other words, a particle or a gas or yourself has to be traveling at least 11.2 times 10 to the 3 meters per second to be able to leave. And then we've got hydrogen, helium, argon, and xenon as the gases that we are going to compare. So first of all, you should be asking yourself, well, if we're trying to figure out which one is most likely to escape from the Earth, what would make something more likely to escape in general? And hopefully you can see that it's got to do with speed. A particle has to be able to reach a certain speed. And the one that's most likely to escape is going to be the one that's the fastest. the faster the object, the more likely it's going to be able to exceed the escape velocity or the escape speed. The next question should be, how do we know which one is faster out of hydrogen, helium, argon, and xenon? If we knew which of these gases was the fastest, well, it would be the most likely to escape. So where can we figure that out? Well, from figure 1, it tells us what the gas speeds are. Okay, so you've got the speed of the gas and you've got relative number of molecules. But what you'll notice is that the graph doesn't actually show us all of the gases that we need to compare, which is hydrogen, helium, argon, and xenon. Okay, but let's just have a quick look to see what we can gather from this diagram. But before we do that, I'm just going to draw another diagram, which is something that you'd probably most likely have seen before. On the y-axis, I've put number of students. On the x-axis, I've put score. And here I've drawn a bell curve, or a distribution. And that's essentially what you're seeing in figure 1 as well, but it's a different type of distribution. But let's talk a little bit about the bell curve I've just drawn with score versus the number of students. This might be the distribution of scores of a class on a particular test. Okay, so let's say they've just had a maths test, and this is the distribution of all the scores. If you want to describe with one number how this class went, you could take the average score. How do we interpret the average score from this distribution? It would be the value directly under the peak. Okay? That's where most of the students would have scored. That is our average score. That point there is our average score. Let's say we had another class and we drew it on the same thing. That could be another distribution curve. Hopefully you can see that on average, those guys did better. Okay? They had a higher average score. Now, with the figure that we have on the bottom here showing us the gaseous speeds versus the relative number of molecules, we can do a similar exercise. If you look at hydrogen, hydrogen is that curve here. The average speed of that population of gases will be around here. That would be the average speed. That's the average speed there for hydrogen. And if you looked at CO2, the average speed is more like there. Then you've got the average speed of oxygen and nitrogen. Okay, so hopefully you can see that. Oxygen and nitrogen. And the thing that should start to become clear is that there's a bit of a trend. There's a trend between the molecular weight of the gases and the speed. So essentially, the lower the molecular weight, as we're going from CO2 to oxygen to nitrogen to hydrogen, it's actually getting faster. Okay, the lower the molecular weight, so let's write that down. The lower the molecular weight, the higher the speed of the gas. We can now use that to solve the problem because hydrogen, helium, and argon and xenon are not on the graph, but I'll just write this out. In table 2, it has listed the various molecular weights for different elements or gases. And you can see that hydrogen, out of all of those gases, has the lowest molecular weight. Therefore, it would have the greatest average speed. And since it has the greatest average speed, it's most likely to be able to exceed or at least meet the escape speed, which is the speed required to escape from the Earth. And therefore, it is the least likely to be retained. So hopefully that makes sense. And you can see how you can break down a question such as this. And there are a few things to note from this question, which is that there is hardly any knowledge that you really need to have prior to doing this question. Yeah, there is a bit of assumed knowledge, which is that you have some familiarity with what hydrogen, helium, argon, and xenon are, which are that they are gases or elements. I guess it helps to know what celestial means, which is to do with space. Okay, but there's nothing really very technical that you need to know. Actually, another thing that is helpful is to be able to interpret bell curves. So with bell curves, understanding what the average score would be or the average speed would be. So being able to interpret that type of graph, that would have been helpful to know as well. But we're not talking about anything really high level science. So yeah, I really like to go through this question because it really emphasizes how important it is to be able to read a question, relate it to the information provided, and to be able to constantly think to yourself, what is this, what is the information trying to convey? How does that relate to the question? I hope you guys enjoyed this video. If you haven't already done so, please give me a like and subscribe. And if you have any questions or ideas for videos that you'd like me to do in the future, please comment down below and I'll do my best to get back to you. All right, thanks guys. Have a good one. Bye.